Okay everyone, in this video we're going to talk about problem 1 from the practice final. So in this problem you're given a grid graph as such with 0, 1 weights. So the edge weights are either 0 or 1. Those are given as input, and you know the structure of this graph is a grid. And the goal here is to find a path from the bottom left corner, which is 0, 0, to the top right corner, which is going to be p minus 1, q minus 1, where the total weight accrued has to be odd. So in particular, we don't want a specific number, we just care that it's odd. And note that this grid's going to be size p times q. So the x-axis will range from 0 to p minus 1, and the y-axis from 0 to q minus 1. So we want to solve this problem, and we're going to do it using dp. So the thing we have to notice is that because we're looking at odd length, there's this natural case analysis that happens. Because if we have our edge is length 1, then when we add that 1 to our total sum so far, we now need even length going forward, because 1 plus even would be odd. On the other hand, if it was a 0 weight edge, then we need an odd path to get an odd path overall. So we can't really just directly break it down into just recursively finding odd paths. We have to find both even paths and odd paths. So one really natural way to do this is to define two mutually recursive functions. This is something we've seen a couple times in study groups. And the main idea here is we can define odd functions and even functions. In particular, odd of xy will be true if and only if there is a path of odd weight from xy to p minus 1, q minus 1. So essentially we're starting somewhere in the middle of our grid, and we want to figure out if we can get to the top right corner with an odd total weight. And then we'll find the same thing for even, except now we want an even total weight. So the reason we're going to find this mutually recursive is because to solve the odd problem, we have to solve the even problem as well, and vice versa. And then what we finally want at the end is we're going to plug in odd of 0, 0. And that's exactly what we want to solve. So we can figure out the recursive equations for this general odd xy function. So first we have the base case. It's false if we're already at the end. So if we're at the top right corner, we have a path of no edges at all, so its total weight's going to be 0. And, if 0 is even, and so we actually don't have a path of odd length. So our base cases will always be false here. On the other hand, let's say that x was p minus 1, which means that we're all the way on the right of the grid. We're on the right boundary. So the only thing we can do is go up from there. So in this special case, we can only have edges where we go up. And if the weight of the edge was 1, then as argued before, we have to call even. And if we can find an even length path, then that path plus the single edge we just had will give us an odd path. And similarly, if our weight was 0, then we need another odd path, starting at that new node. Okay? And then when y is equal to q minus 1, this just means that we're at the very top already. So we're up here, and now all we can do is go right. So these are special cases, and it's the same kind of idea in both. So for the general case, we have much more flexibility. So we can either go left we can either go right or we can go up. So this is a right move, this is an up move. Now, whether we want evens or odds will depend on the weights. So now I'm going to define W1 to be the weight of the right move and W2 to be the weight of the up move, just to simplify the notation. So if both weights are 1, then we have an or. We can either take the right edge or the up edge, But either case, we're going to need an even path going forward because we just added 1 to our length. Similarly, if the weight of the right edge is 1, then we have to have even for the right edge. But if the weight for the up edge is 0, then we need odd for that. And similarly for the other two cases. So we can break it down into this case analysis depending on the current weight and whether it's an up or a right move. And then we can define even similarly. So it'll be almost the same thing, but you just flip all the odds and evens, and the base case will now be a true. And then at last, we return odd of 0, 0, as I mentioned before. So the nice thing about this is, it's very clear that odd of xy is going to take, there's p times q total subproblems. Each of these will be constant. And so if you already have computed even, it'll be easy to compute odd. But this odd even clearly is very large and messy, but that's kind of the idea. So we can actually write this in a more compact form if we use modular arithmetic. So in particular, we're going to define this exists function that takes a point and this additional parameter a. And it'll be true exactly when there's a path from xy to p minus 1 q minus 1 of weight a mod 2. So essentially this a parameter is telling us if we want an even or an odd. So if a is 0, that means we want even weight overall. And if it's 1, we want odd weight overall. So if the total weight is odd, then mod 2, it'll be 1. So that's equivalent. And if it's even, then mod 2, it'll be 0. So that's why we can do this. So we're essentially combining even and odd into one function by adding this additional a parameter. And then by taking mods, we're making it so that number doesn't grow too large. So that's going to be our exist function. And we want exists 0, 0, 1 for the same reasons before. We start at the bottom left corner, and we want the parity of the overall path to be 1. So now we can define recursively our exist function. So the base case is when we're at the top right corner, and then we can find a path of that parity if and only if the parity was 0. So remember, for odd, if we're already at the end, we can't take any more edges, and so the total path length is 0, which is not odd. However, if we want an even path, then it should be true. So recall this is Iverson bracket notation, which just takes the predicate inside and turns it to 0 or to true or false. So this is just saying, if a is 0, then this will be true, otherwise it's not. Then we also have this extra case where if x is bigger than or equal to p, or y is greater than or equal to q, then it's just false. So this is just saying if we go off the grid, false. Because of course, there's no valid path at all, let alone one of the correct path parity. So the reason we define this in this case and not in the previous algorithm with even and odd is so that we can make the general case much simpler. So in particular, we can break this down into exists of the right edge and exists of the up edge. So if we don't have a right edge or we don't have an up edge, this will become false. So we're encapsulating those previous cases before, these special cases here. Those two special cases are built in to this new base case. Now the general structure of this says either we take the right edge or we take the up edge. And if we take the right edge, we know that the parity we need going forward might change. So recall that when the weight of this edge is 0, we want an odd length path, in which case we have 0 plus a would be 1, which is 1. Mod 2 is still 1, so we get an odd length path. On the other hand, if this weight was 1, we get 1 plus 1, 2, mod 2 is 0, representing we need an even path going forward. So using these mods will give us a simple way of encapsulating how the parity changes as we see edges of different weights. And then we have the same kind of idea for the up edge case. So either we take a right edge or we take an up edge, and depending on the specific weights, we either need an even path or an odd path going forward. And that's what this recursive relation is telling us. Okay, so that's what we're going to work with now. So we want to use dynamic programming, so we've gotten the hard part done. We just need to go through the tedious work of putting it into the iterative solution. So the first thing we need is our data structure that holds all the subproblems. So notice each subproblem is encoded by x, y, and a. So x is always between 0 and p. We can never get more than p because we always get this false base case the second we hit p. And similarly for q, for y will always be between 0 and q. And so we have a three-dimensional matrix with enough entries to hold all these xy pairs. And then we also have this just two-item extra dimension for a, which will be 0 or 1. So this is actually a constant slice. So you could think of this as a three-dimensional matrix where one dimension is constant size, or you could think of it as two matrices, a equals 0, 1, and an a equals 1, 1. And this would follow our intuition before of having an even and odd recursive function separately. But it's whatever you prefer. They're both equivalent. So now we want to figure out which subproblems depend on others. So we need to figure out the dependencies graph, basically. So usually you might draw a picture to do this. In this case, it would be a cube, but one of the dimensions of the cube would be constant, which is kind of weird. But luckily we can just figure out what the order should be without even drawing anything. So notice we always depend on a larger value of x or the same value of x. So we have x or x plus 1. So clearly we need to solve larger x values first. So we need to compute x starting from p minus 1 and going down to make sure that we have the larger x already completed when we're at our current subproblem. And similarly, we want y or y plus 1, so we have larger y's, and so we're going to loop from y starting at q minus 1 and go down to 0, so that we have all of our larger y's done first. So we have xy is done in this way. Then the order of a doesn't really matter. So as long as x and y are computed in the right order, a could be computed in whatever order you prefer. So you could do the zeros first, the ones, it doesn't matter. And so you can translate this into a triple for loop where you have this is the x as the outer loop, y is the inner loop with these bounds, and then a is the inner loop where it's, say, 0 to 1. And then you just plug in the recursive function in that loop. And that will give you the iterative algorithm. So the running time is the total number of subproblems, which is p times q times 2, which is O of pq. And for each such subproblem, we do a constant amount of work, because we just have to do an OR and then a mod 2. So overall, it's going to be O of p times q times O of 1, which just gives us O of p times q total.